Neurotechnology is a rapidly growing field. It combines neuroscience and engineering. It focuses on understanding the brain and nervous system. This field aims to develop devices and therapies to treat neurological disorders. It also seeks to enhance brain function. Neurotechnology includes brain imaging, brain stimulation, and brain-computer interfaces, or BCIs. Neurotechnology offers hope for millions. It can help those with paralysis, blindness, and other disabilities. It can lead to new treatments for conditions like Alzheimer's and Parkinson's disease. The ethical implications of these powerful technologies require careful consideration. We must ensure they are used responsibly and for the benefit of humanity. Brain-computer interfaces, or BCIs, are a revolutionary neurotechnology. They establish a direct communication pathway between the brain and external devices. BCIs allow individuals to control computers, prosthetics, or even their own limbs using only their thoughts. BCIs work by acquiring brain signals, processing them, and translating them into commands. Signal acquisition involves recording brain activity using electrodes placed on the scalp, which is non-invasive, or implanted in the brain, which is invasive. Signal processing involves amplifying, filtering, and decoding the recorded brain signals to extract meaningful information. Finally, output devices such as robotic arms or computer cursors execute the commands based on the decoded brain signals. Non-invasive BCIs, primarily based on electroencephalography or EEG, are safe and convenient. EEG records brain activity through electrodes placed on the scalp, detecting electrical signals generated by neurons firing in the brain. These signals are then amplified, filtered, and analyzed to identify patterns associated with specific thoughts or intentions.
EEG-based BCIs are already being used in various applications. These include controlling computer cursors, wheelchairs, and even playing video games using only thoughts. While EEG-based BCIs offer excellent temporal resolution, capturing brain activity in real time, their spatial resolution is limited, making it challenging to pinpoint the exact source of brain signals.
Invasive BCIs, such as microelectrode arrays, offer higher fidelity brain signal recording. These tiny electrodes are surgically implanted into the brain, allowing them to detect the activity of individual neurons or small groups of neurons. This direct access to neuronal activity provides a much clearer and more detailed picture of brain function.
Invasive BCIs have shown remarkable promise in restoring lost motor function. By decoding the neural activity associated with intended movements, researchers have enabled paralyzed individuals to control robotic arms and even regain control of their own limbs. However, invasive BCIs pose risks associated with surgery, device rejection, and potential damage to brain tissue, requiring careful consideration and further research.
Section 5. Machine Learning and AI in BCIs. Machine learning and artificial intelligence, or AI, are playing increasingly vital roles in advancing BCI technology. These algorithms can analyze vast amounts of brain data, identify complex patterns, and improve the accuracy and reliability of BCI systems.
Machine learning algorithms can adapt to individual brain differences, improving the personalization and effectiveness of BCIs. They can also learn to recognize new brain patterns over time, allowing BCIs to expand their capabilities and adapt to the user's evolving needs. The integration of AI and BCIs holds immense potential for developing more sophisticated and powerful neurotechnologies. Section 6. Restoring movement with BCIs. BCIs are revolutionizing medicine by restoring movement to individuals with paralysis or neurodegenerative diseases. By bypassing damaged nerves or muscles, BCIs can create a new pathway for communication between the brain and the limbs. In groundbreaking studies, researchers have demonstrated that BCIs can enable paralyzed individuals to control robotic arms with remarkable dexterity. Participants have successfully reached for and grasped objects, poured drinks, and even fed themselves using BCI-controlled robotic limbs. These advancements offer newfound independence and improve the quality of life for individuals with severe motor impairments. Section 7. Treating neurological disorders. BCIs hold significant promise for treating various neurological disorders, including epilepsy, Parkinson's disease, and depression.
Deep brain stimulation, or DBS, a specific type of BCI, involves implanting electrodes in specific brain regions to modulate neuronal activity.
DBS has shown remarkable effectiveness in managing the symptoms of Parkinson's disease, reducing tremors, stiffness, and movement difficulties. It is also being investigated as a potential treatment for epilepsy, depression, and obsessive-compulsive disorder. BCIs offer a targeted approach to modulating brain activity, potentially alleviating symptoms and improving the lives of individuals with neurological conditions. Section 8. Enhancing cognitive function. Beyond treating diseases, BCIs have the potential to enhance cognitive function in healthy individuals. Researchers are exploring ways to use BCIs to improve memory, attention, and learning abilities. For example, studies have shown that non-invasive brain stimulation techniques such as transcranial magnetic stimulation can enhance working memory and attention span. BCIs could potentially be used to create cognitive prosthetics that augment human capabilities, improving our ability to learn, remember, and process information. Section 9. Revolutionizing communication. BCIs are transforming communication, particularly for individuals with severe disabilities who are unable to speak or move. Augmentative and alternative communication devices powered by BCIs allow these individuals to express their thoughts, needs, and desires.
By detecting brain signals associated with intended speech or letter selection, BCI-based AAC devices enable users to type messages, select words from a vocabulary list, or even control a speech synthesizer. This technology provides a voice to the voiceless, empowering individuals with severe communication impairments to connect with the world around them.
Section 10. The ethical considerations. The rapid advancement of BCI technology raises important ethical considerations that must be carefully addressed. Privacy is a paramount concern, as BCIs could potentially access and interpret our most private thoughts and emotions. Data security is crucial to prevent unauthorized access to sensitive brain data. Informed consent is essential to ensure that individuals using BCIs fully understand the risks, benefits, and potential implications of this technology. Additionally, equitable access to BCI technology is essential to prevent exacerbating existing social inequalities. Section 11. The future of BCIs. The future of BCIs is brimming with possibilities. As technology continues to advance, we can anticipate even more sophisticated and powerful BCIs that seamlessly integrate with our bodies and minds. Future BCIs could enable us to control our environment with our thoughts, communicate telepathically, and even experience virtual reality directly through our brains. However, alongside these exciting possibilities, it is crucial to proceed with caution, addressing ethical concerns and ensuring that BCI technology is developed and used responsibly for the benefit of all humanity.